new. Okay, welcome to Euler hack number 9, hosted by Next Tuesday. Whiteboard is there in case we need to draw anything. This is being streamed to YouTube, so your faces won't be visible, but your voices are recorded. The notebook here will be posted online, and you can review if you want. Toilets are to the right of the entrance, next to the lockers. And yes, drinks and biscuits and stuff. So the format is that we have problems here, lots of them sorted in increasing difficulty, and we pick one and everybody starts from the same page. And so we start with picking one randomly. And you do have the honors, John.
For picking one.
Yes.
Problem 8.
Problem 8.
Is a solution in there?
No, it's just it's basically this thing here.
The problem is oh, jeez.
If you can hand those out.
It's 4 times the second. 4 adjacent symmetrical papers in it. You have it.
Hallo, ich bin Manuel. Masu? Masu. We already started. For your info, we're being recorded just your audio, okay?
Problem 1. Find the 13 adjacent digits.
The largest product in a series, the 4 adjacent digits in a 1000 digit number that have the greatest product. The 4 adjacent digits. Are they talking about this particular number
No,
here?
no, that is a given thing. And the question is find the 13 adjacent in this 1000 digits that have the greatest product.
Right, but
You have to find the
1000 digit number they're referring to in both cases is this thing here.
The same thing.
Yes. Okay.
That's a programming thing.
Uh-huh. So the 4 adjacent adjacent digits. So I'm going to find somewhere in here 9989.
No, but
Yeah, there it is.
yeah, but we need 13.
Right.
Now we need
Right.
The question is 13.
Right. Yes.
13.
Right. But this is just the test. So if we search the same problem before,
You will get that. We should get that one.
yes. Okay.
Yeah, programming.
Just,
A series of 13.
and series size.
All zeros can fall out, of course.
Pardon?
If there is a 0 in, you can skip the whole
Yes.
series.
Right.
And the zeros are a lot of them in it.
Yes.
So you all already need to start with defining the series that have.
Let me just.
So actually you have to split at all zeros. And you have a certain.
Let me just pick that out so I don't have to write it multiple times.
You can do it manually. Replace the zeros by an enter also. Is that possible?
Okay. Well, okay, how do we go about this? Yes, we can split by 0, but that's not the general solution, I guess.
We can take starting from 0 and take up to the n.
Okay, so
Here and
okay,
yeah.
I guess that's true.
Yeah, but the next step could be taking the next one and deleting the last dividing by the first one of the previous one and take the next one.
But you still have the product.
Yeah.
The moment you add the next digit to the product, you actually need to multiply it with all separates.
No, we don't
to
need
make
to.
it quick.
If we have 1 to 13, we multiply it by 14,
Yeah,
but divide by the first one.
you don't have millions, but if it would be million numbers, you need to keep all products separate and add them.
No, we
Well,
don't need to.
You can reduce complexity by, as you said, split them by 0.
Yeah.
Like in every split, we can produce this algorithm, like going by step and check.
No, that doesn't reduce the complexity though. It is order of n.
No,
What I'm saying is order of n, and we cannot make it less than order of n.
because we can like do split it, and then we can have parts less than 13, so we can like exclude that part.
Yeah, but still it will be order of n.
Less.
It will not be less than order of n.
If we split it by zeros and we have parts that are the length of these strings less than 13, so we exclude all that part.
And still,
But you
complexity,
you see that in advance if you make your algorithm detect that.
Right, but this is kind of, I think this is a
Yeah.
termination
It's not-
condition.
Yeah.
Isn't this, it's
That's
like if we have some recursive solution, we go through each digit. And if there's a 0 among the digits that we're looking at, we just terminate at that point.
Yeah, and start again at the next one. Yeah.
Well, we go through all of them anyway.
Yeah.
So, yeah, okay. Okay. Will we have a problem? I mean, we're going through... okay, well, the worst case is we start here and then we go down, 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 down. I guess as far as our number here. So 4 in this case, or 13 in the other case. Right. So this is the max that we look at, and once we reach that, we collapse down and go to the next. Is it? I mean, this is the brute force solution.
Yeah.
And since it's problem 8 and difficulty 5, I assume it's tractable.
Yeah, even brute force n is equal to 1000, so it's not like
That's tenths of a second.
even n to the power of
Even in Java.
5, it's
Even in Java, it is quick.
Let me do strip and I guess replace all new lines also. Where's my backslash? I think my backslash is
Yeah,
broken.
but leave the original series also intact.
The original series?
Yeah, the digits itself.
There's my back. Come on, give me my backslash. Where's my backslash? English, German keyboard. Something's wrong here.
Old 92 it is.
it's
No,
next
num?
to the enter, the X.
Well, okay. Well, I'm not
It
using.
is the right bottom, I think.
If you are using English keyboard,
I know my keyboard. Something is wrong.
Make it English keyboard.
Oh God.
The German keyboard is the right Alt and the 7.
I know where the. Okay.
Yeah.
This is not going to go well. I already see. Okay, no problem. Okay, we'll replace this with the empty string. So now we have a continuous string of digits, I believe. And I guess we can.
And replace the strip. Replace the 0.
Replace the 0. No, we need to know that we need to keep the zeros. We need to know the
you
termination.
first need to have it in one row.
Yes.
Ah, yeah.
Yes. So here I guess I'll create a list of a map and map to int. So I think this should give us all the numbers. I'm not sure about the bracketing. 1, 2. 1, 2. Should be okay. Okay, let's look at it differently. Let's do this first.
Yeah, it indicates. But
strip to remove what?
That is.
I bet this is some kind of weird
Spaces.
copy and some kind of white space issue.
Yeah.
No, it's not.
Maybe
Or can you
no,
see
no
this?
strip?
Why strip? Strip is not
Just to get rid of these backslash ends. Okay, right, you're correct. Because of this, we don't actually need this.
Isn't this enough for us?
Wait, I'm not there. I don't understand this. Why? Okay, whatever. I can go digit by
Maybe
digit.
because it's
I can go
like-
digit by digit. It's no problem.
Yeah, of course. Because it
This is valid Python.
the program can process this. It's not a million digits.
It will process in like 3 seconds.
Yeah.
3 seconds.
They
This
should
is a
have
cha-
made
sounds
it
like a challenge.
now take the first million digits of pi or so, and then
I mean, we have to define the method product.
Yeah.
you can trust that Python will, that the computer itself will.
Yeah,
see
sure.
zero.
Fine. Yeah, of course. Yeah.
Can I
yeah.
have it?
Okay.
We converted the mapping map to int you have done, then
So what are we looking for? We're looking for so we just passed the digits, I guess. Digits and series size is, let's start with the 4. So we go, what is it, 4, I guess. Well, you wanted the product, right? Def product is I guess digits again, and we already have ints, so
Position.
p is 1 and 4d in digits, p times equals d, return p. Huh?
yeah.
So for I guess sub digits in, no, this is first of all I guess, sorry, pardon me. I don't want to give you ability, not on purpose anyway. We go len, well, I guess range, len digits less yeah. Sub digits I to I plus series size. Okay, and looking for the largest. So
now you have I until. Yeah. It's not counting the last one in it.
is it not?
I don't know that digits array.
This is exclusive the last, yes, but it should be.
Then it is okay. So there's no -1 necessary. Okay.
Yes. Well, let's see.
Receive maybe.
Yes. And product.
Maybe we product.
Was that the? Yes.
Yeah.
Okay, so let's start
I
13.
would modify the variable digits
Why?
in product and in
I can let me do this.
part or no, make it part or so or a section or
It's still digits, right? Yeah, it doesn't matter.
I would.
You mean just
sub,
to?
sub. That is it. Yeah.
And this is okay for you?
Yeah,
Well, it
that
is always yes. Okay.
Local.
See, take only 1 second. I don't know whether the answer is
Oh,
correct.
let it tell the position.
Much less.
That's
The
what I asked.
position.
That we can find it where it was, and let it highlight and let it.
Now I have to pull this out. I have to pull the eye out
Yeah.
if I want to find this.
Yeah.
Okay, let's do.
Maybe
We can do this.
return to-
We can do this.
Max.
Yeah.
So it has calculated them all. You just don't know which the max. Is there no other result than max? That the max does not return the
It returns.
position in the array.
Oh right, I need to convert it to string. I guess. Map. So this is the one. This sounds like an issue. Ah.
So you may not be finding it.
So
You're
new
kind of
line.
you're breaking it, yeah.
Yes, line. Oh god, I hope adjacent digits. I hope they don't consider new lines as an issue.
No, then you need to put in a 0 everywhere instead of the
What do you mean by new line?
So the string isn't being highlighted here.
Find,
So-
find only the 557.
So maybe there's a new line here.
No, find only the 557. That should be enough.
Yeah.
It should not occur more than.
Yeah.
Okay.
You found it.
That is it.
I don't know if this works.
668,
Probably not.
966.
Okay. Well, there it is.
Yeah.
Yeah.
That is it. Yeah.
But first, let's check whether it's 13. Maybe it's not.
Yeah, it is. It is 13. Yeah.
Yeah. Okay. Okay. Something's correct.
Yeah. Okay, so they actually wanted the product or the substring itself. What is the value
I would,
of the
I
product? They
would
want the
like to
product.
see the position.
They want to see the product.
Well, the position. Why? It's here. That's the position.
I would like the program to return the position.
Why? What use?
Because all other data are not interesting, actually. Yeah, of course, it's the only question is what is the.
I don't know.
No, find the 13 adjacent digits. So
Yes,
which are these?
Yes, they don't want the
That-
position.
Find the 13. What is the value of the product? That's the
Yes,
question.
they're looking for this.
Oh yeah. What is the value? Of
Well,
the
let's see whether it is the actual one.
These. Probably the code is not valid by now. Come
I
on.
think you haven't.
Yeah.
Yeah, we have it. Huh.
You are the 263.
200 and.
You know, that it'll be cool if then
Can
your
you-
position is the number of is the answer also.
That would be extremely cool.
Oh,
That would be a trick in the website. What was the other solution?
Nice.
Sampling.
Whoa.
yeah. I think this is. Yeah,
Not
coding
fun.
golf, least amount of instructions. Yeah. All right, let's look at the actual.
Search on the night. It's not.
No, there's not many
Oh, yes.
nines. 2 nines in
Are
it.
you looking for a large number at the end? I
Yeah.
guess.
Not necessarily.
No.
No,
Not
you're,
a, yeah.
you're
Maybe
looking for
at right, not at
a series with almost no ones and no twos and no
Yeah.
threes,
Yeah.
because those count. Say the 5 to 9
Yeah.
count extremely stronger than a 2 or a 3.
Yeah.
someone with Java.
No, but looking for 9 is not going to. It's not like viable because you can have like
Well-
12 nines, 1 0
The
in between.
nicest thing would be to take the logarithm of each digit and put them in a graph and just find the highest point or the highest integral of, say, the highest.
You mean the actual products or just the digits here?
Take the logarithms so that you only have to do plus.
Oh, right. Yes. Well, okay, but then you have to do the logarithms.
Yeah, but only 9 times, 10 times. Yeah, 9,
All right.
8.
Sure. Okay.
No, but then we'll have to still go. We are not going to escape from order of n.
Yeah.
Yeah,
You cannot skip from
still,
it.
because then you don't have products.
No.
Yeah, of course,
the
order
product
of n, of course, but
the product we did can be really made much smaller by. We take the first 13. I'll probably go there and show. Alright. We take the 13. This is the string matching algorithm. I don't know, which I forgot the name. We take maybe this one.
Sure.
Mode 1.
There are also black ones.
Yeah. 1 to 13. We have the product. Then in the next loop, we will take p times digit of 14 divided by digit of 1.
But
Yeah.
that is a very slow.
Yeah, actually you could
Calculation in the
reuse
computer.
this stuff, couldn't you?
We use it in many other places too. But in that case, we will have exactly maximum of n minus m multiplications where n is the largest and m equals 13 for us.
Yeah, and you need to account for the 0 because you cannot divide, so you need to skip that one.
So whenever we have a 0, we can skip all the way.
Yeah, you have
You
to
can just
because
jump
you can
over.
never divide through it. So
That's one thing. That times it is a benefit to us. It's not a loophole. It's like we can jump over that automatically.
But if you know the multiplication takes 10 times as long in the computer
Yeah.
to calculate, and the division even 20 times as long.
But also
And you have
the
converted
logarithm
the whole
is also
series
taken,
in one time.
This
What I'm
With
saying-
logarithms, and you
what
do
I'm-
only add additions.
What I'm saying is, even if we do that, that is going to be a constant change. It is not a asymptotic change. We still have to do everything 1,000 times.
True, but you make the program an addition series.
When
so,
you-
so if it is 10 to the 40th, you at least only have to do additions.
Yeah.
And
But
not
when you convert
multiplication.
this number to logarithm, also do multiplication. Or no?
Yes, but only
Yeah.
9 times because this is a
9
digit.
times, it's all-
9
it's all
times,
single digits.
and then you have a lookup table. And then you only do addition of these 9 logarithms. You know?
Like doing this.
So log of 7, log of 3, log of 1, log of 1, 2, 3, 4, 5, 6, 7, 8,
You're
9.
doing it only 13 time or
No. 9 times.
Only replace all digits by its logarithm.
I mean,
Yeah.
So
the-
for the
here,
whole and for
here,
10 times.
instead of, oops, sorry,
Not-
can you move a little up?
Oh, but math log.
Yeah, exactly. That's what. And you can
For
mem-
1000 times.
No, you can memorize that. So
Yeah, you could. Yeah,
when
exactly.
you memorize that, 7 comes, it gets converted only once. The next time you look up.
Okay, we can do.
Yeah, so you have to.
We can do what we do. We can do something like
Time it.
base 10 logs is I guess
It's an array of.
math or is
Yeah.
yeah exactly, it's an array of. So we start with yeah, we'll do math log and for n in orange 10.
Yeah, but 0 is not possible. That's
Yes.
so it's
We'll-
a
we'll-
0 for the 0 and a 0 for the 1.
Yeah, let's just do 0 plus, and here
And
we'll
the
just
and the
start
1,
at
and you do n in the range 1 to 10, 1 to 9.
It's
Oh,
it
yeah,
is
of course.
exclusive
Yeah.
always. And here, instead of doing this, we can do, I guess, index. No, it's like get item, I believe, or something. Bullshit. Okay, so let's see. What do we have here?
So-
Let's just do it separately.
We have 2 zeros then.
That's, well, one thing after another. So here we have 0. No, we don't have 2 zeros. We have,
Yeah, that is a 0.
it starts at 1. Yeah.
No, but that's first
Yeah,
zero.
the 1 is also a 0, yeah.
Yeah, and actually we could also convert these to integers because all that matters is that they are scaled proportionally, is it?
Yeah, so you can do them times.
And then we would only
10
be doing integer arithmetic.
times 10.
Convert them to
Because that
integers.
is-
Yeah.
Yeah, so times 10 now. Times 10 is probably
For
Is-
n?
is
yeah,
sufficient.
enough, yeah.
For n or
Because-
for the log?
No, if it is n, then you have to do it
What
by
is
100.
what is the biggest difference? The
100
smallest difference is in the
100
4,
and
as in
the
the 9 and the 10, of course. Oh, the 8 and the 9.
Yeah.
And that's now a difference. Okay. That's
Okay, now I can do.
Uh,
So will this change
this
the
is
result?
margin stuff. You need to do 100.
This is you need to do 100.
You never.
10 is not enough.
Yeah. You're never sure because.
Will this change the result, or am I correct in this with the scaling
This
thing?
is close enough.
We hope. I mean, it could be that the 4, 5, 6.
And then you have to do another map to back
Yeah, this is not going the right way.
to get the
No, you
product.
find the position.
Right,
of
get the
course.
product. The product
You
is.
find the position.
Yeah, you find the position and then you can do the product. So we're thinking of arbitrarily
Make
large.
it 1,000 because it can never be exact enough.
Okay, whatever. Okay, and then log digits will be something. I'll get it. I guess I have to serialize it. And I wouldn't have to, but let's just do it. Okay, so then we have our logs, and then we can do, I guess, products.
Can you also print the base 10 logs? I just want to have a look at them.
Okay, let's print. Aren't they pretty? Let's just
Rounded.
for the.
Is it rounded already?
It's floored into floors it.
Oh, yeah.
Okay, so there you have your pretty digits.
Just want to write it down. 7, 6, 9, 3, 1, 7, 3.
And let's just, I guess, do this. And instead of product, it's, I guess, plus. Jesus
Yeah, and
Christ.
0 is now, you need to detect it because otherwise.
Yes. Right.
Because the 0 cannot count at all.
Why convert them to
Or just fill in
logarithm?
minus.
Why we just don't add them?
Just fill in
Because the
minus,
biggest
minus
product
20,000
will have
for
the
the
big-
0.
Because or not.
Because we want to do integer
Yeah,
arithmetic.
just fill in minus 20,000 for the 0. Then a sum with the 0.
We are going in the wrong direction already.
You know, there are other problems. It's not
exactly.
as if we have
Yeah,
to do
that's-
this.
Yeah.
Why we are doing the logarithm? If
with
we
this
just even add them instead of doing the product, we will end up with the same result.
You think?
Yes.
You said
Just
you
replace
think even
that.
here the plus will do, or what you're saying?
No, the 0 in it
It won't. Then the zero, when there's a
Yeah,
zero,
the
it
0
will be
is a
like-
problem.
is counting as a 1, so you have to.
But in the algorithmic also will make a 0 problem because it's considered as a 1 also. Because we have for maybe for 0 when we change it to algorithmics we change it to minus big number because logarithm of 0 is minus infinity.
More than, of course, 13 times the 9 number.
You probably should return 0 there instead of p.
Right. And here I need to start at 0, I guess.
Yep.
Yeah, it doesn't matter actually.
I would be surprised if this produces the same result, to be honest. I mean, it won't produce the product, but I guess we're looking for the 557.
Yeah. I think it will. No, it did.
What does it do?
A big number. Big. Okay.
The 1.
Oh, that's not it.
975 3. Where is the 975? Take the other one. Those two occurrences.
It must be somewhere else. It must be
No,
9,
there
7.
was 2 found. So you have
Here,
to,
this is it, I think. 975369 5369. Yes, this is it.
What is it?
Here.
97.
This is what it says.
That's only. And what is the product?
I guess I'll
Yeah, you don't have it anymore.
Yeah, okay, let's right.
Let's call that sum instead of product.
Yeah. This can stay, this cannot stay. This is times,
Yeah.
and then I can do from this insert below product, I guess.
Like that.
No, I have to do comma.
It has to be.
Or maybe string.
Yeah, I have it now. So this is 8.
I think
and
one order less than ours.
so let me just product here again, just so we can compare. So is this larger? No,
Yeah,
it's
one
not.
order less.
Yeah, it's a lot less. And this is also, I guess, than 13. So it's not, this is not a way to success.
How can that be? Let's with this thing. There must be somewhere a little. Oh, you did not make the 0 a minus. No, there is no 0 in it.
Yeah, there's no 0.
Oh, there is a 0 in the. Oh,
Where?
No, there's no 0 in it.
No 0.
Why it's not?
Why is it not giving the same?
Well, I don't know, you want to go through it? It's like, so you have a 1 in here and a 3 in here and apparently 9. And if you weight the 9s here or something, I don't know. It's different.
So
what can I say?
It's 9 and 9. There's 3 9s and 4 7s and an 8. 5 7s. And the other one is. Yeah, but there is a 1 in it. That does not count at all.
Yeah. Well, once in the sum at least. But in the product it's one. It doesn't. Yeah.
Yeah, but in the sum also not, because there is the list of the log of 1 is 0.
Well, this is just the sum digits. This is nothing that we don't.
What was the largest what sum?
Here. No, sorry, here.
Yeah, but you got the largest sum of all those. So that's not. So you need to calculate the product of that instead.
Well,
again.
that's what I did here. That's what I did here. So here are the actual digits, and this is the product, which is then this. I'm declaring victory, and we're moving on.
Yeah. Yeah. There must be some stupidity in it.
Here, this is why the distribution to be the sum and product does not have to be matching.
I will be back in a minute, and you can.
There is 3 times 4 times 5 is 60. 3 plus 4 plus 5 is 12.
Okay, no, but we do not add.
Can you explain
no,
what the
It's not like
But we do not add the numbers. We only add the logarithms of those numbers. It cannot be.
No, it's not an explanation kind of that way. Your question is, we have a set of digits. We are finding the largest sum of them, but they do not match the largest product.
Yeah.
So this is like, this probably points in that 3 times 4 times 5 is 16. 3 plus 4 plus 5 is 12. Now let's keep the same thing. Take 1 from here and put it here. 4 plus 4 plus 4, it's still 12. But since the numbers changed, 4 times 4 times 4 equals 6.
No. The principle of the logarithm was to.
No. I'm answering his question.
Of course.
So here these two have the same sum of digits. They don't really correlate to the product.
Yeah.
That's why now what is the mathematical reason behind it? I have no idea. But we're just looking for an example. And I think that's the problem we have here.
Yeah, but this is exactly the difference. The 5 becomes a 4.
Yeah.
That's 20% less.
Yeah.
3 becomes a 4, it's 25% more.
Yeah.
33% more.
Yeah.
So that 20% less, 33% more, just gives back a number.
No, I understand that. This has nothing to do with logarithm. I said,
You made point that of course the sum and the product may be different, but
they don't correlate.
Yeah.
Yeah.
That should be, there is counterexample where you can find like higher product but less sum.
Yeah, exactly. I mean, so when we do the sum of digits, that's probably the reason we have a larger sum of digits, but that doesn't mean it's the largest product of digits.
Yeah. Exactly. Okay, Sandeep, please.
51.
What? Primes, always with the primes. Okay. So of all two-digit numbers, we replace the first digit, which is the rightmost digit, I guess.
Yeah.
And then we have 6 of them which are prime.
56.
Jesus Christ.
Wow.
I need. So we're only looking at numbers which follow the pattern 5, 6, star, star, 3. Is that correct?
No, I think
No?
we are looking for all possible families by
8 possible.
Yeah, but the family should provide 8 primes when we replace.
Yeah.
Whoa.
How
So
long do
how
you
do
think
you-
this number?
How
What is an 8 prime value?
No, it's
Eight prime
the
is-
family of
The
8.
family will have 8 primes in it.
That is in the 2 digits was example was 6 are prime.
Yeah.
In the second in the 5-digit number there is this example has 7. Now find the families of 8.
Yeah.
Yeah, how do you determine whether the family is 8?
We'll have to do that and see whether it is.
Yeah, so it's again a programming problem and go through the masses.
Well, I don't know. Probably there's.
Is there?
Well, I won't say anything because I don't understand it yet.
We will have to start with. We can generate with a
Something like that. Like you have a number when you can replace 8 numbers.
2 digits by the same. It was very important.
Some machine is burning.
Oh shit! It is indeed very important.
So sorry, Atef, you were saying something?
I was saying, for example, you have like a number, something like that. I don't know if it's could be 3 same number or something, but you can generate from this by replacing the stars by the same number,
Yeah.
family of 8 prime numbers.
Ah, okay.
Yeah.
So it's about replacing 2 stars somewhere. Is that what?
Yeah,
or
here
more
it's
stars. Could be two,
replacing
could be
2
three.
stars. And you get 5-digit number, but could be 3 stars to get
The 8.
Still 5-digit number.
8-digit number. Yeah.
Okay. By replacing the 3rd and 4th digits with the same digits, this 5-digit numbers. The first example having 7 primes among 10 generated numbers. So among all the numbers with among all the primes which match this, 10. It has 7 among the 10 generated numbers. It has only 10 numbers, so there are only 10 primes
Because
which match
replacing
this.
the same, yeah, from 0 to 9. Because the star is the same number.
Yeah.
So from 0 to
Ah,
9,
right,
like
right,
2
right,
0
right.
to
Okay.
1s to 2 3s, like 7 from these 10 numbers are 5-digit numbers.
So there are 10 numbers at all because 0, 1, 2, 3, 4, 5 and so forth, and of those 7 are prime.
Yeah.
Yeah.
Okay. Being the first member of this pi is the smallest prime. Okay, so they're looking for the smallest of those, and we want to find, but we do need to find all 8 of them, otherwise we don't know that it's the smallest of the 8.
Yeah. We need to figure out when we replace, we should get 8 of them as prime.
Uh-huh. But they don't tell us how many times we replace something.
No, it could be 1 or 2. I mean, it doesn't even have to be adjacent.
Right.
That's the worst of the worst part.
Panic?
Suppose
No. Okay.
Suppose you have 6. You need to do it with the 6-digit numbers.
Yeah.
But it could also be that there is already a series of 8 in the 5-digit primes. 5
Could be.
go off. But suppose 6. You need to list all primes of 6.
No, that's not too difficult.
And then find all overlapping numbers so that you have, and then determine if there is a series of 8, because there are lots of series of maybe less or more than 8 the same. So
Yeah.
you need to put all digits in a row and count them all. And then also the overlap, that's impossible.
Should we?
Then each combination of the first, the second, the third, fourth, fifth, sixth number, that's impossible.
It's impossible.
It is
Difficult.
Yeah, no, not difficult. It's a lot. It's just tedious.
How about a tree? Should we look some kind of tree thing? So we start with prefix tree kind of thing. So we at the bottom is 5, and then above it is 6, and at some place we say we can branch around or something.
Oh, it has to be the same number.
Yeah.
Well, it has to match this pattern.
Yeah, a pattern like that.
Yes.
But we don't even know.
But if it is 5 digits,
Yeah.
you just need to have the 9 different digits.
But they could be in any place.
You have to find all primes with at least a double digit in it. And then 5
Does-
It doesn't have to be double.
Yeah,
it could
does
be
that-
not adjacent.
Yeah,
not
it
necessarily
must be the
adjacent.
same digit. You have to replace
Where does it say not necessarily adjacent?
with the same digit.
Last line.
Last line.
Yeah.
All primes which has at least, the same digit repeating somewhere.
Okay, how about we do the other way around? We just get ourselves all the primes,
Yeah.
and then we just generate whatever patterns and see if
That's what I was doing with my eyes.
how far did you get?
I reached 3,209.
Is your battery life not worth nothing?
No, I'm not writing program. I download the list I was looking. If there is a pattern I can see.
There is no pattern in the primes. Is there no other property or so that you can say if they if they are at the last position, then you have. If they're next to each other, you can divide by 11 or no. Or,
It's prime, right?
Well,
yeah, it's you can divide that part of the number.
Yeah, I think the best solution is start generating a whole list of prime numbers
can.
and
well, okay, that's the easy part.
Yeah.
Uh,
Generate the list to start with.
We go into our big book of cheats. Well, I don't know. I think probably I can pick one at random, and we probably have prime here. Here we go. Okay, so we get some primes. I guess I hate this. Okay, we call this make primes. And
I still don't get it why they call it replacing. You don't replace. It is a prime bit.
No, they are replacing that digit.
Yeah, but it is already that digit. That is the prime number.
No, we don't know which that digit is. So we have to find a digit, star, some other digit. The star will be replaced with, first we replace with 0, then with 1, then with 2. We'll try all of them. And so we will have 10 of them, of which 8 of them should be prime.
like same length and
No,
we collect
no.
Yeah, it is. It could be that the stars need not be together, they could be split in 2 different positions.
Yeah. Maybe we start create has
Three.
has 2, 3, 4.
It's
Maybe
not
start
2.
with 3.
It's not 2 because I tried 1 and 7. 3 already have. They all have only 6 primes. It's at least 3.
3. Okay.
okay, so
Function has 3 similar numbers. Has 4 similar numbers. I mean, create a function to test.
okay, so
No, it's not the 2 digits that.
So what do we have in here? I guess just
We should in every step like test if it's the same length and
Yeah.
has, for example, 3
You know-
same
you know
numbers
something-
and the length is
You know something more?
Pass me water.
The smallest of these, of course, has 2 zeros or 2 ones in it.
Likely, very likely, yeah.
No, not
sure,
like it has
because
to.
it's an 8 in a family of
Yes.
8.
One of them must be
0 or 1.
right. There can only be one missing.
No, there can be 2 missing. So it's a 0.
Okay, well then it can be 0, 1, or 2.
Yeah.
Yeah.
Okay, but that's true.
what?
The pattern here. So you notice it says we have to replace the same digit 8 times. So the set of these primes is 8 long. And if that's true, then the smallest of these, well, not the smallest, not necessarily the small, yes, the smallest has to have either 0, 0 somewhere or whatever.
Why is it?
Well, at least it has to have 2 zeros or 2 ones or 2 twos.
Yeah.
Assuming it has 2 things that are replaced. It could have
Yeah.
3 that are replaced.
And then you can check if the one with replacing the one up and 2 up, you can start trying.
Yeah.
Yes, if
There's no other way than trying.
No, we have to try. No,
I
that's
think
a good,
so, yeah.
Good clue. We find the 2, 0, 2, 1, 2, 2.
yeah.
The first one of that pattern which fits, then we can try to replace that.
Yeah.
See whether we have 8, otherwise we go to the next
And
one.
then make it efficient, also try the 987.
Well, we just
That
Yeah,
doesn't matter.
exactly.
we
It doesn't
abort.
matter.
We still
Yeah,
have to do all the
generally speaking, we go through and we abort when we have when we have 3 misses.
Yeah.
Generally speaking, right?
Yeah, if we have 3 misses, then we are alright. Yeah.
Yeah.
Okay. Okay, so what is we start with the little function, I guess, that does the one case. Let's do, I want something that has, I think this,
56003.
You enter the number of.
yeah. So I give something, how do we do this?
No, 5600. Yeah.
0, 0, you want to have this as a placeholder?
That's the prime number that you'll find.
So this is the lowest prime number. No, well, this is one that we'll find, right? But what is the? I don't even know where to begin with in terms of the function that we're trying to write. Is what I'm saying. So, like, I have to have some kind of pattern as an input, right? I mean, something like this. I don't know, and presumably, hopefully, not as a string.
Yeah.
I could.
That's what I said. Like we write function that does check has two similar ints, has three similar ints, has four similar ints.
Yeah. Okay. Well, one of the
It's one of the test.
similars, or I guess I don't know. Does it have a number here? What does it call it?
The replacing number, so the rep number.
Num replaces is 2, I guess. And I guess we'll call this the pattern.
Replacing part of the number, so you might have, if you
Yeah, exactly. Okay, well, let's just do it this way, and I position things anywhere in here, right?
first it's not.
Well, it could be.
Yeah, anywhere in there, yeah.
It
No,
could,
no, because when you start with the 0, you have.
no, it doesn't. That's just one miss.
Yeah.
Okay. Okay, is pattern. Okay, well then I guess I don't know. Okay, well we go through our digits. 10, I guess, and we're going to generate a candidate somehow.
Try the 0.
And then we're going to well, it's probably going to be something based on the num places.
Maybe do pattern dot count equal dot count d equal to 2, like for the whole. We don't test pattern, we enter pattern, just we will enter the prime number.
Yeah.
And
And
we'll
we'll
check.
create the, yeah.
We'll check. So we don't enter pattern.
Oh, you don't try all. You start with finding a prime number.
Well, I mean, so far I'm trying to. I mean, we have to go look at these digits, and we're going to replace here 0. We have to go through combinations, right?
Yeah, but
I think because we are making primes, just pass the prime to this test pattern and check, for example.
Okay.
First check if it has like two num replaces equal to, or
I don't know. So what do you want to check? I mean,
I meant like run this function for the every prime, like loop through primes and do test.
right? No. We will generate the prime.
Okay.
I think. I mean, first of all, we will generate the prime candidate. Candidate, and we will do
Dot append or something.
if prime candidate in primes, then we do, I don't know, matches.
I thought we
I
already
think
looping
better
through
work with-
primes,
work
so
with the
we
list of
don't
primes.
check.
It's less numbers to check.
What is less to check?
Just work through the list of primes.
If we loop through list of primes, we don't check if that pattern is prime or not. We just loop through primes and check in every prime match that
Yeah.
check or not.
Find the number of zeros.
Or zeros if you don't have, then ones.
And
And
then
until
ones.
3, if we don't have 3, then we are done.
I'm not following. Maybe you want to do this?
He wants to. I volunteer here.
Okay.
There should be at least 2 zeros.
Or you can try the whiteboard, but I'm not. Okay, you want to go over the primes. Okay, so for P in primes,
Yeah.
and you want to do what?
Just count the number of zeros. In the
And
number.
why is this supposed to be faster than generating the possible candidates and checking if they're prime? Why is this faster?
Because
we only have the
otherwise
primes,
you
right?
have the whole million numbers to check.
Well, I have a million primes to check, don't I?
Yeah, but if
But you will be checking also non-primes. You go through all of them. In this case scenario, you will go through only the existing ones. For you, it's like pattern match and prime.
You don't need a million prime. How many? How long?
Yeah, well, I can abort early, right? Yes. If
Yeah.
P greater whatever, then break. Or return false or something. I don't know.
Be greater than what?
I don't know.
Say million. So try the numbers
Well, it
until
depends
6.
on the number.
Yeah, but try first.
depends
First
on
let it run until 6 digits.
Well, okay, wait a minute. So the max P is len pattern plus num replaces, and this 10 to the power of that, right?
How do you need?
Isn't that it?
Yeah. Yeah. And
Okay.
equal does not exist because there is no power of 10 prime.
Sure, but I mean.
No.
Okay, so
What is that pattern that you want to?
I don't know. You tell me.
Maybe we
That
can-
is if you start,
we
if
can
you
check-
generate, say, the list of 10,000 patterns and add 2 digits at random places in it.
I think to make clear, maybe we can call this function check candidates. There is no but.
Yeah, okay.
Okay, and we look through primes.
And we don't care about the pattern, I guess.
Yeah, we don't.
You find it. You will find it.
But now I need to keep track of the common prefixes, right? Ah, but they're all consecutive. They're all next to each other, I guess. Are they? No, they're not.
Yeah,
No,
they are
they're
not.
So I guess I'm looping here at this level.
You have to find a string function that finds the 2 zeros in the number.
To find.
That's how you want to do it. You want to check for the two.
Yeah, that's why I
It could be 3.
for the in
Yeah.
if
It could be
3.
and that's difficult. Then you have to
no
check
we
all
can start.
combinations.
That's why I said we create function of checking, like there is 2 digits, same digits in that prime number. There is 3 similar digits. Okay, so we do for D in like range 10, we do if P dot count D equal to 2.
Yeah.
First check if there is 2 zeros in it.
Well, this is the general thing he wants to do, I think.
And if you have 2 zeros or 2 1s or 2 2s,
and let's, I guess, do.
then you can check the other ones out.
Yeah.
So if
P dot count dot count D is equal to num replaces.
right.
Then it's candidate.
Okay, and they want to collect all these.
Yeah.
Yeah, but
We have to check the length of the prime. We keep it, for example, prime of length 4, for example.
You want to keep, okay,
We
so
don't-
we
we
want
don't
to, you want to have
abandon-
it indexed by
Yeah.
the length?
Yeah.
Yeah, makes sense. Okay. I guess collections default.
yeah, but if you have found one that has from the 0, 1 or 2, then you have to do a totally different procedure to find out if there is the other digits also at the same position in the list of primes.
Well, okay, we know we have, okay.
I didn't understand.
You find if there is a double 0 or 1 or 2 in
Yeah.
it,
Yeah.
and once you have found such a number, you have to do a totally different procedure to check if you replace the zeros by ones, that it's still a prime, and
We loop through primes,
yeah, but how?
so we are sure that this number is prime. So actually, if
No,
match
you
this,
only-
it's a candidate if match this condition.
Yeah, but you have to find a set of 8 candidates.
Yes, that's why we did this collection of. We don't.
Yeah, but still you don't. You only need to find finding the candidates.
Yeah, we found the candidate and then we check.
But
in
you
that
find the
dict-
candidates with also double 5s and 7s and 9s. So actually, then you can find.
Alright,
You have your whole 8 family already in your candidates, also with the double 6 and the double 7 and so. But you reduce the number of candidates if you only search for the 0, 1 and 2.
Is it also not correct? We're right, it's correct, yes. Okay, fine. If we look for the 1, then this is, right, these are the candidates for this issue here, right?
See, what was it?
So for number places 1 and the length 2, we have candidates jene.
That is not possible, it should be all digits. Oh no, all primes. Oh, this is also all primes, yeah, of course.
Maybe you can.
Because
make
the
it
number
a set-
place is only 1, so
Yeah.
this is all primes
Yes.
below 100.
Yes.
There is an error in this thing because it's not delivering the 11
Make it a set, maybe.
and it's delivering 17 double and 19 double. What is this? It's all numbers are double.
Interesting.
You have 2 times the print in the
Well, we
thing.
go over here
Yeah.
multiple times.
No,
So I guess we can
Oh,
break
yeah, of
here.
course. Yeah, of
We
course.
can break here. Right.
If you have,
Once we find it,
yeah, of course.
we have it.
Still 11. It is not showing. Why not?
I don't know. Oh, because it's twice.
Only once.
Oh, it's a big.
It shouldn't include this thing itself.
No, it's greater or equal. You have to. Greater or
Yes, because it could, the number could already be in there.
Yeah.
You know,
It could be 2 times. It could
one
be
of the
one time
digits that we're not replacing could be the same as the digit that we are replacing, as in the case with 11.
more. Yeah. Now, but give it. That doesn't. Yeah. And now something else is you can stop at 41.
You mean, for example, if we are looking, it can have like three stars, for example, and
Yeah.
we can makes sense.
But you can stop at the D in the 0 to 9. Because you know that you only need candidates.
Well, no, because it could be that for one replacement, it's...
Now from now on you're only searching the candidates instead of all primes.
Yes, exactly.
Maybe that's quicker. Yeah.
Maybe. I don't know how much...
Try for len 3.
For
And
len
number-
3 with
yeah,
one
and
replacement.
with 2 replacements yet. No. Because otherwise it's all primes again.
Isn't this all primes?
Yeah, but now num replaces is 2.
Okay.
Candidate length is okay.
Now you have only the length 3 with 2 the same digits.
Maybe.
Yeah,
Can
sure.
we do 7 and number of replacement 4?
Are you sure my console won't break?
Then it's I think 7.
That will not work.
Oh, let me see. Let me just limit it a little bit for just as precaution. So 7.
Number of
you
replacement
you limit the
2.
you,
There 2.
you limit the number of primes with length 4 by 1,000.
Yes, this is just for the
Yeah, but
print.
there are no 1,000 primes under 10,000.
Sure. Okay, I thought there was going to be 7. Okay, sorry. Or
Oh,
something like
7.
that.
Yeah, of course, make it 7.
Is that what we want?
Yeah.
Yeah.
First 6 thing, I think.
Nothing.
Yeah, because the least the smallest one is 5,000 from the question.
Yeah. Oh, you can bring it back to 5.
The smallest
Yeah,
one is
that should be found. That should be possible to find it.
It was well, I only have up to 6 digits in here, so that's why I only did so many primes.
There are more than 1,000 primes under 10,000.
So I only have 100,000 primes. That's why the 7
Why is this
match
order
nothing.
of numbers of output so different? It starts with 65537.
Because it's no, I don't know. Oh right, because it's not sorted. It's not sorted.
Huh? The primes?
Yes, it's because I thought we can do something different. Prime list. There you go. Happy?
Yeah. See if the 56003 is in it already.
Well, it probably is.
That has to be there. Otherwise, we are doing something terribly wrong anyway.
What are we looking for? 56003. That's yeah. 2. Okay, well, okay. Now we have some candidates. I guess we go. Now we're looking for. Now we're generating patterns. I guess.
Now you search the candidates with.
Okay, for P in candidates of length so and so. Well, I guess we go through the length maybe. Well, let's just try 5 at first. Okay, okay, for each of these prime strings, we want ones that are common to each other. We can't do this way.
You can do it in the break. Yeah, I mean you can find.
No, let's do it this way, because this way, if we do it in here, then we're not sure that the other ones are in there yet.
Yeah.
Here we know that we have all of the ones that are of length 5. Okay, let's just do, I guess, for len, or I guess num digits, comma candidates in items. So here we have the candidates, and we can also search them now.
Is this automatically calling the function? Only if it is needed, yeah, of course.
Which one? This?
Items, yeah.
Right, this is only called once. And then the for loop uses the return value of items.
No, I mean, is it, for example, for num-digit? What was num-digit?
This is
The key.
The key, yes. Len, okay, I guess len.
PSTR.
Yeah, let's just call it that. And let's call this PSTR. Just to be consistent with up here. And also then PSTR up here. I guess we don't need to calculate it every time.
What is
You want to call it len?
what is PSTR then?
For prime as string.
Oh, that's your length of your number, but then as soon as you get to
Well, if we only need to consider candidates which have the same
we
length.
don't create for the candidate prime by len as two-dimension thing. We have the len and the for example 0, 1 or 2.
I was trying to do something
Because-
like this. I don't know if it makes. I think he wanted something like this. So this was like I took 1 0 and 1009 1013. These all are primes. Then I looked for 2 0. So I was looking whether any of them again repeat. So I just wanted to see whether second digit can be. The first digit is the possible one. So if we can make, like, x, y direction, we have the numbers here.
I mean here,
Okay.
like,
what did
we
you
are already looking for.
I couldn't get enough.
So-
I've another strange idea.
So then we have the
Let
len,
me just listen
for
to the
example, equal to 7,
Yeah.
equal to 7 and different.
Yeah.
So from here, because we already populated this and we have different.
But actually, you already have.
And DM is different. For example, here is 7 and D is different.
Right. Okay,
Yeah.
so now we can go through. Right, we can go through all the candidate by, I guess.
All candidate primes of the same length.
Okay, so now we go. Okay, for I guess Alt D in. I don't know.
It's E.
Okay, sure. Well, no, but it's a digit. Okay, let's call it D1 and D2. How about that?
Yeah,
Are we
that's
satisfied?
super. Yeah.
Okay,
Why
and
don't you start with D0?
Yeah.
and I guess if
No, you
they can
have
be
to-
the same, right? They can be the same digit?
Yeah, of course. You need now to check that it is exactly 8.
Wait, but this is we need to have D2, 3, 4, 5 in theory. Yes, this is so good. Well, this isn't an array, so
No. You only,
leave me alone.
no, digit 2 is.
No, but in the general thing, this is just comparing two digits, right?
Yeah.
Yeah.
So it could be, and also this doesn't solve the first digit issue. It is in general,
Wait.
is it?
It's like also another loop. It's not like.
Okay,
just
we're
D2.
fine with manually coding the
Mhm.
loops. Okay, fine. Okay, so yes, and now we know okay, so this is the D1 candidates, and this is the D2.
No. Let's just leave it. The candidates is the candidates.
No, it's not.
No.
No,
Yeah,
it's
because
not.
No,
No.
but you don't make a new list of candidates. You just check if you replace.
Yeah, that is the D2 For that we need a second set of candidates.
Right, now we know all of them which are candidates which have D2, right? So these and these. You know?
Yeah.
And now I guess we look for the intersection or something?
Oh, just do it in the same loop. In the same loop, you just create. How big is that candidates list? You just need 9 candidates
we
lists.
take the intersection, yeah.
You make 9 candidates lists, and you find the intersection of those all.
That's what it's doing.
You only have to skip the same, otherwise there is the intersection.
What? Yeah, okay, the intersection will in one case be all of them, right? So in some case this will be... So if we're looking at the same digit...
D2 in that minus D1. D2 should loop through all those numbers except D1.
Yeah.
Except D1? Why except? But they can be
No,
both.
even
Yeah, I mean, we will have the duplicate, it's fine, we have an extra, it doesn't matter.
It's
Imagine
a
D1
candidate if D2 is different to D1.
Okay.
And there is a very, very tricky trick if there is 2 zeros in the number. and actually the ones that are in the number
yeah.
are the ones that start the series. Then you're missing it. Because you start with the...
No, but then they are
Is
not
this
3
notation
5
is
numbers.
to store this as a key?
If you have
This
6,
like
1,
to
1,
start
0...
Yeah, this is
yeah,
a
that
tuple.
is the zeros never at the end. But if you have
And you can
6,
unpack
1,
here.
0, 0, 1...
Yeah.
Like
We will still have that.
It
I
could
would
be
like
that
to
the
start
ones are the
with
ones
that
that
and-
do the list of
I'm
2,
not
3,
sure.
4,
That we
5,
will
6.
get. That we will
to
get.
store D as a
We'll see.
value, not
I don't
as a
believe
key,
it yet.
Okay, why?
and then you can
Oh wait,
because if it's
yes,
different,
yes. If it's different, we shouldn't break here, right? If it's different, we can't break.
we can't break.
Before we did break, but that was when we were looking at only one list of
You
things.
only need the candidates with a 0 or a 1 or a 2 double in it. That's anyway.
The D1.
The D1, the first list of candidates. The start.
Okay, so if D1 not in... is this a string even? Yes, it's a string. 0, 1, 2. Is this what you're saying?
Yeah.
Yeah.
Plausible?
Mm-hmm.
Plausible. Okay.
And then D2 can start at... yeah, the 0 you can leave out, but that is not relevant.
Okay.
No, you cannot leave it out because it could be that there is indeed.
It's fine, we will do a little extra loop, so what?
Yeah,
We are not
Well,
losing anything.
We haven't executed any code in 5, 10, 15 minutes, so we're not good.
and it is not.
Let's have it running first at least.
Okay. Really? Did it? What? I'm not manipulating anything. Where, what?
What's there?
Oh, oh god, this is...
You're looping through it, yeah.
No, wait.
I mean, you're looping through D1 candidates. No, you are not.
Right. Where am I manipulating something? I don't believe him.
Check candidates.
Where was the error?
Here's the error. Dictionary change size. So he claims that the candidate primes len changed.
Candidate primes by len items.
Can
Yeah, make it manual. Just start with
Oh
5.
wait, because
When you access it?
yes, when I'm accessing it.
Yeah.
Okay, I need to first convert it to a plain old dict. Yeah. Okay, this is tricky. Dict items. Okay.
No, it's the same variable name. Oh.
Yeah. This is converting it. So the thing is,
It's a Python magic.
yeah. So
Yeah,
this
of course,
default
but the
dict.
same variable, I don't like that.
Yeah.
It has 2 types in your program. No.
This is just a reference in both cases, so I don't know. I think it's, in any case. So
Like
this
a strongly typed language, it would not
Yeah.
be nice. Yeah.
Unless, I mean, in Java you could just say map of thing to thing. It wouldn't mind either.
No, true. It
No,
replaces
I'm
the
fine,
variable until that moment.
In any
it
case,
is,
the reason why this is failing is because default dict, just accessing a member or an item will actually create
That's it.
the set, which happens here because for cases where this thing does not exist yet. So we convert it to a thing, and this means we will get a key error. Okay, so I guess.
Hey, you got a key error.
Okay, so I guess let's just check. Or not in. Well, why is this happening actually?
Because we are going through all the possible numbers. They are not in prime numbers.
Okay, so this would be the case, for example, where 0 is the last digit, I guess.
Yeah,
Yeah.
for example.
Well, okay,
No,
yeah,
it
for
there's
len
a-
pister 1 and where the thing is the last, I guess.
Yeah.
Okay. So, am I running out of memory yet? No. Okay.
You're done.
What was that? What was the bottom? There was a few strange.
So what am I printing here? I'm printing the D1, 2, and the number of candidates for these combinations. So for 2 and 6, there are 7 candidates. For 2 and 7, there are 25 candidates.
2 and 6 means?
Did I actually I should print the len pister also. So for numbers of length 5
Yeah.
and considering D1 and D2 be 2 and 7, there are 25 candidates. That sounds...
You only need 1 candidate. It doesn't matter. There are candidates or not.
well, common candidates.
Yeah.
So, right.
But you only need 1 common candidate.
I need
Not
to-
one
It should be the same common candidate for all other digit combinations. But you don't know
Okay,
that.
well, this is... let me just print them out because apparently it's not...
I was
too
thinking
much.
of a little bit different approach.
What the hell?
Yeah, the first is empty set, but
Yeah.
you can scroll down just.
Oh, that's a little messy.
Okay, for numbers of length 5 and with these 2 digits,
508, that's what we probably want.
these are the candidates. 508.
No, we need to print. I was looking for the length.
Five
Can you also
seven
print length as well?
What is the
527. We should.
What is
check
the one?
527.
5 to 7.
Yeah, our candidate should be or not.
No, but then I want an 8. We need 8.
it is wrong. It is wrong.
No, I mean for the example.
The intersection is wrong. You see that? You now have numbers that have 2 zeros and 2 nines in it.
That's fine, right?
No, you don't need those. You need the ones that are in the set of primes with the 2 zeros at the same position as the 2 nines.
No intersection.
So you need the 2 different primes that have the 2 zeros and the 2 nines at the same position.
No, that's true. You're right. But this is, we have already made it smaller. Now, we are looking inside this for the same location. It's easier. That's all.
This 56003 is not in it. Because you don't have, you have search for intersections with 2 numbers in the... Because you're now searching for primes that have 2 zeros and 2 sixes.
Correct.
But that's not the thing.
Yeah.
It should be if the sixes are in the same place as the zeros. So you have to find 2 different primes.
Yes.
Yeah. So you have to replace the sixes by zeros. Oh, that's
Maybe the count and check for
just
the
go through
indexes
the primes
is the same.
and try to replace the zeros that you find by.
But sometimes we may not have the zeros, maybe it's 2 ones.
Okay.
Yeah, but you have to do
One
it for
zero
the
for one
zeros
subject,
and you have for the zeros you have to do the whole.
Okay, but this is much more. I mean, I have to go over all of the
At
candidates
least that
here and
intersection
replace
that
them.
that is not the right thing.
Yeah. Okay, let's just forget that this ever happened.
It is if you have.
I think if we go back to the checking the number of counts, we should check. I mean, for count, maybe we also have the same
Actually,
indexes.
the way he's saying it is,
John?
here we go through and in the candidates we replace D1 with D2 and check whether it is.
Yes.
Yeah.
Yeah, but
Check
for each
whether that is-
candidate, right?
Yeah, for each candidate. Yeah.
And check whether that is also in the list. Yeah.
Yeah. Then if we
And
have,
we count the number and we increment as long as that happens.
we can probably keep a miss count. If we have 3 misses, we can get out.
Yes, exactly.
Yeah.
Okay. Okay, let's try that. Misses. Oh wait, what about the case where we're
When you
replacing
start
multiple?
with the 2, you already have 2 misses. Oh yeah,
And we also,
you will
it's
reflect
not
them, yeah.
also not enough to replace them. They have to be in the same position. We have to replace them in the same position.
Yeah,
Only-
when you replace D1 with D2, it will be always in the same position, right?
But not for. We have to also in the same position for 3, 4, 5, 6, 7, 8, 9. They also have to there be in the same position replaced.
Yeah, because when we loop through D2, that will be right. We will take D1. We will take the candidate, replace D1 with D2.
It's only.
What do you mean string replace? Or you mean index? We have to replace the index.
Is there a number?
We have to go through the
String
indexes.
String replace.
But then it won't be at the. But then I mean, if we replace 0, 0. Okay, we're going through these candidates.
Yeah.
So 0 here in this case is here,
Yeah.
and here and there. But we're always looking for the same positions.
Yeah, but we have to check whether it is in the prime list. If it is not, we already have a miss.
Okay, so you want to okay.
If it is in the candidates list.
Yeah, candidates list. Yeah.
So if it's in the candidates list, we can then look further if they're in the same position also. Is what you're saying?
Yeah, that will
Okay.
happen automatically through D2.
Okay.
Once we have 3 misses, then we can go to the next one.
Okay.
In fact, yeah.
All of this sounds like
No, it sounds like it is not the right approach.
Yeah.
It is a working through thousands, millions of combinations and just.
and it's also
find it.
very fiddly.
We have gone the wrong way from start anyway.
Yeah.
Yeah. Do you want to take a step back and
Yeah.
maybe reconsider?
If you do say binary, you have of course positions. This one and this one. This one and this one. Like binary,
Tree.
like binary numbers. No, like just
Positional digits.
positional.
Okay.
This one. Then it starts with then it is this one and this one. Then this one and this one.
This is what I said,
This
prefix
one, this
tree.
one. This one, and then is there more? No, it's always the same. It is though. It is like this, isn't it?
He did suggest that earlier, right?
So this is digits. Digits 1 and 2. If you start here at 1, digit 1 and 3, then 2 and 3, 1 and 4, 2, 4, 3, 4, 1, 5, 2, 3, 5, 4, 5. So you have actually, this is the thing that you need to check in all these candidates. And then, of course, 1, 2, 3, 4, 5, and 6, all the positions. And hope that you by 6 positions have found your result.
You're describing a recursive algorithm, I guess?
Yeah, you just start searching with for a prime.
Yes.
With
starts with 1.
With 0, 0 in the last 2 positions.
Okay, you start backwards, is what you're saying. You start with the rightmost digit.
Yeah. That is what I mean. Also the right side. Start with finding a prime. No, that one does not exist. But
well, we iterate forward. We get to the 1. Yes.
A 1, 1, and find if there is a prime with 1, 1, and if that exists, you try 2, 2 in that same place and go to the list of 1, 2, 3, 4, 5, 6. Just try them all.
Yeah.
But it is indeed better to have the candidates already because
What about their storing the indexes by using the binary sum? Like, for example, if we have like 2, not sure about it.
Binary sum, is this a term I should know about?
No.
Or okay.
I mean like to know the position of 2 digits.
Yeah.
No, but we can probably try to continue this way. We already have something there.
Well, okay.
But now you still have to try all combinations because there could be a number with 4 ones in it, and you don't know which ones you need to replace by 2s and 3s. See what I mean? You have to try all combinations. So if 6, 1, 1, 1, 1, 7 is a prime, you don't know which you need to go trying. If it is 6, 2, 2, 1, 1, or it is 6, 1, 2, 2, 1, you need to start trying them all.
Okay, I have a feeling I will need iter-tools combinations.
Yeah, maybe for example, like to store in the candidate prime length. For example, if we have 2 zeros here, so we have like 1, 1 here. We store 7. We store like this equivalent. It will be store 6.
Oh, of course, fill them in all. Fill the table.
And then if
Fill the
there is
table.
like
Eureka?
Yeah. The table is very limited. You see that?
Do you have a solution?
yes. Okay. So for example, if we want to check for this, we have like five digits and replacement 2, and we want to also store in the candidates the position of these 2. So the position will be, for example, we mark it as this 1 and 1, and it will be like binary sum, so it will be 6. So also store this.
I'm not sure what you mean by binary sum.
Yeah. You just use it as a binary number.
But I mean like binary number, not binary sum.
But
For example, if we have like and the next one, for example, for D, if
we shouldn't convert them to binary. That won't bring us to anywhere. Because there is no pattern for binary and prime, right?
No, but there is something.
I mean just to store also the position of these 2 numbers. Like
You want the position? The position you want to store.
Yeah.
Okay.
So
I mean store the position. For example, if the position
Yes.
is here,
Right.
so we store also 6.
You want so the pattern. So the pattern is this binary sum.
Is
I
the
see.
binary number, yeah.
Fair enough.
So in that case, we have in the candidates, we also have a field where we are storing the position of these
Okay,
numbers. We have, they are different, the same. So at our check, we check the same position but are different,
Yes.
and then it's the number that.
Okay,
we
so
need.
do we want to?
Maybe
so
here we
It
do
is
like
this. You have
we
this
store
6.
the index here.
Right.
pstr.index d.
Well, we need to go multiple times, right? We need to. We need to get all indexes, I guess.
All indexes. Of
So
all points.
yeah. Okay, so this is
Put
Of
to the
all
power
primes with
plus-
each number.
That would be something like that.
and yes, and the pause would then be
2 to the power of
The pos, the
pstr.index is dot d.
yeah.
Yeah.
This
yes.
Maybe because we are through this loop, we add the pos plus here, because this loop through all the d's.
No, I'm not sure.
You need the position of the number 1 for each candidate. And then
Yeah,
the positions of the
yeah.
number 2 for each
Yeah,
candidate.
because it can have 0 in other places, but we don't want to count it.
I don't know.
You
Yeah,
know-
because this or more, so it doesn't make sense.
You can make a table for the 1s and for the 2s until the 9s, the 0s too. All primes. You give them a binary number that represents actually the positions of the zeros. So,
Positions. Well,
the
the
zeros. Say if the number is 790002 3,
yeah.
then you have here. Actually, you convert
0, 0,
it
1,
into
1.
Into this one.
Yes, yes.
12, 13, 14, 15. 15 is all, and it's 14. So this is 14.
Yes.
And now you find the ones. Okay, 0. 2s, 0. 3s, only 1.
Yeah.
4s,
7 is 2 to the 5, I guess.
Yeah, I guess. Yeah.
6.
Anyway,
Yes.
you have all these candidates, but you have the positions.
Yes.
The moment that you get to the next and the next and the next, you have to do AND of these numbers.
Well, we have to.
And as soon as the AND delivers not enough positions anymore, so it gets.
Yeah. Okay, so we have.
The issue is, for example, if we want to track only 2 replacement, but here we have like 3 zeros. So it will be counted 14 as indexes, but we want it as 6.
We should probably time box it.
You know what I mean?
Yeah. And I have this was
But I think this is promising.
Yeah, this is a good idea. I had another thing that was this list you can also easily fill, because this is only 20 until 6 digits. That is the just find, and that times of course also for the 1, 2, 3, 4, 5, 6, 7. This is the other way around. That is, you take these 2 positions and you check how many primes there are with the 1 in these 2 positions, and not how many. You just record the list of candidates with the ones in these positions, and the list of candidates with the ones in these positions, and then check it again for the 2s and the 3s. So you make 20 lists of candidates, but you only select, of course, with the ones in this position, and you have to check 20 different positions.
Well, let me think about it differently.
And it's a pity that you cannot do a binary AND on.
We could do
on the
something
digital
else.
number.
We could do something else. We could go through the primes. Then we go through each digit that we care about. Then we do this, generate these indexes. and we
These. All these.
the
I think this
the
one is
binary
small, this
indexes,
one is,
the binary indexes, and the way we store it is we replace those positions with x, so something that isn't a digit, and that is then our key for the candidates.
Yeah. I mean, for example, for only we have here two replacements.
Yes.
So we want to store, for example, these two replacement. For example, the two replacement are here.
Yes.
For example, if we have 0 here, it's also candidate, but in the indexing process, we will count it as like should be, for example, 6, but here we count it as 14. Because here we only can detect, we also should detect which are superior than number places. That's why we may.
I don't think it matters the way we, right? So let me try.
If we can calculate the indexes without any problem, so it would work.
There's no rule.
Let me try and
solve it programmatically, right?
There's no what?
There's no rule we have to solve it programmatically, right?
No, I don't think there's a rule. So what I'm thinking about is let's just look at this.
I have a better solution.
So
I know, but like.
So first of all,
if it's up to 4 or 5 digits.
Yeah.
So we're looking at this number.
Look this candidate list separately manually without programmatically generating.
Let's assume that this is a prime. I don't know if it is, but
this
let's
list
just
of
for
it
argument's sake assume it is. Or we can just take this thing from above.
Possible two positions.
Yeah.
And just make a list of candidates with at least these two numbers the same.
So we don't actually need the index. Maybe we don't need the indexes.
Kind of.
So I could generate this by doing simple replace multiple times. So here I could end up with I don't know. Let's just do 0 and I don't know. Let's assume these are also prime.
No, this is multiples. So this, you check the candidates with on the last two positions, that is 11. Yeah. This is the position with 101. And you
Maybe
just
you can change the pattern to follow the
you
example.
add 101.
Vice versa.
Here's the example
and
from
and
the.
see if that is still a prime, and add another 101.
You mean
Because
So-
this position
X are here and here is
Yes.
6 part.
So when I'm looking at this
as 10
candidate,
binaries, but
I replace the zeros
Mhm.
and with pardon me. Yes, I know what you mean. Pardon. So we wanted
If
to
you-
have this 6 and 0 0 would be XX 3 and likewise here, but only once. Okay, and assuming all of the so we're looking at this number.
Yeah.
We replace 0 once. We replace 0 with x twice.
Yeah.
And each time the replacement is used as a key,
Yeah.
and we add on that candidate as to this list that we're tracking. And at some point we get to this, at some point we get to this, and so forth. And then all we have to do is go through these numbers and check for the length of this list.
Yeah. So here we store the length of.
So you only
here
need
these, for example, here it's.
Well, the length is kind of implicit, right? So the number of we could just only do number places.
No, because it's 7 digit for this 5, because the number should be the same for all the list to be candidate. I mean, the candidate prime we only check if the length here is the same for the.
But that would be implicit, right? Because the replacement will always have the same length.
Okay.
yeah,
maybe
I was to put the count of occurrences at the 56xx3.
Count of occurrences. What do you mean?
If you find the 56003,
Yes.
you fill in the 56xx3, and you say, okay, this one has now a count as 1. If you
We
find-
add it to the list.
but the first time you find it, you add it to the list
Yeah.
and say count. If the second time you find the same 56xx3,
Yeah.
you add it to the list, but just not add it anymore to the list, now just increase the count of the number at 56xx3.
Well, as long as I know that I'm always only looking at them once, that would be true. But I'm worried that
I think it's different approach. Here we are having like different patterns. We're trying to find the candidates, but at first we was trying to loop through a whole primes and with some checks to.
You still have to go through all these combinations, because if you happen to find 61117, you still have to try it on this one. So this one XX, you need to fill in 61XX17. You need to fill in 6X11X7. You have to again.
you have to do it 10 per candidate in this thing.
If
I have to do 10 replacements.
If the number occurs 3 times, you already have 3 combinations. If the number occurs 4 times,
Well, we can try. We can try, and we can hope that. I mean, here we're below 100,000. So if we hope maybe that the number we're looking for is below 1 million, then we have to maybe do 10 million. We have to have this thing with 10 million total entries, which might work. I think.
No, the less. Then of course you have to.
I think it's.
Well, of course, less. Yeah, on order of, let's say. Okay. It's less, of course.
And you still have to fill in the x's at different positions if you have the number. If you have 3 6s in the number.
Right, but this is simple. This is just take this number as a string and replace 0 with x, replace 1 with x, replace 3 with x.
No, wait.
And do it twice every time.
When do you get an input number?
Here.
Yeah,
Well, this is it. This is the input. So here I go over the D, and now I say Easter replace D max num replaces and candidate, let's say by pattern.
Yeah, but it is.
And the pattern is this, and we replace it with x. I believe that's how it works. Let me just check.
Yeah, but that is a way of going through all these patterns again.
I think maybe so. Is that wrong? S replace. It only works if you have the object. So yes, you can specify a count. Okay, cool.
I guess it's not the best because you have to.
How we create these candidates?
And how do you create your different patterns?
Well, here. Okay. Well, I need to. Well, there are multiple. Let's look at this number. How many different patterns for 0 are there?
Yeah, here there's only 1.
How many are there here?
The fifth one, there's already 3.
Right, okay, so this is a good point.
There's 3 patterns. And if you have 4, then you already have 6 patterns to fill. So I would say just
but this is possible. I
make
think
a list of all 15 patterns below million. And just fill and
No, that's
check
assuming,
them all.
That's assuming we have only 2. There is probably 3. We are going with, there are 2 digits which are the same. They have never said it's 2. It could be 3.
Yeah.
It could be just 1.
Well, it's
So we have to generate it anyway.
yeah. So this would actually generate this pattern, right? Because I'm doing number of places, which is 2, this would actually generate this pattern.
Yeah.
But if there's a different thing where the thing is x, okay, so I don't know,
So
conceivably.
you actually have to go through all, say, binary 2 numbers under, say, until 6 digits, so 64,000 combinations, and let them apply to all prime numbers under a million.
Yeah.
Whoa. And then hope that you find the group of 8. And I suspect that someone who has done this already properly, that there is only a group of 8 in some 11-digit numbers or so, and there, and it's three numbers, that one and that one and that one.
I have a feeling that this is less than 10,000.
Actually, that is kind of maybe worth going down that road. What would the solution possibly look like? Because
I guess it is a number like 7, 6, 0, 1, 0, 2, 0, 3, whatever. And this 0, that can be 2 and 4 and 6, 7, 8, 9.
Are you skipping 3 and
It can. You can have exactly 2 skips.
The
Why
number
would-
we are looking for is less than 100,000.
are you sure?
20.
I'm sure.
projections?
I'm sure of not, because otherwise it would not be. You could just look through the list and just recognize it.
It's not that easy. I mean, it's less than 100,000. There are 9,500.
Is there no transformation that makes them recognizable?
I want to ask
Between
Mario
two
something
numbers.
that this would make sense.
Well, this is I think what that is.
Take
This
the
is
differences.
this is the transformation. This is the transformation
Position of X
that makes them recognizable. But we just need to generate all possible patterns.
I would say don't call it. Next.
I mean, the line I like the most is for nums in it dot combinations. I like that line because we have to do something with that. Because I'm considering this here, for example. This put all the primes into a file, and get all the 4-digit primes into a file.
Well, okay, list.
Yeah, a list. It's a file because I'm going to grep it.
Oh, Jesus Christ! Well, there is the regex module, you know.
Yeah. I mean, that's complex. This.
the same regex.
I do have the regex. Okay. So you want to generate?
No, if you
want to
this-
generate regexes?
Like, if this makes sense, that's all I'm saying.
Of course, it is possible.
Yeah. For 0 to 9, all digits, we look for this pattern. This is the pattern he created.
Yes.
If grep this pattern in this 4 digits and count WC minus L, if that count is L8, we are done. So we have 6 patterns here for less than 10,000.
Okay.
For the next, for 100,000, we use his method or some like similar method to create all the possible combinations where 5 digits X can appear anywhere,
Yeah.
5 digits X can appear in
Yeah.
2 places, 5 digits X can appear in 3
Yeah,
places.
regex could be a solution here.
Then we do
So-
the same business.
So the
Change
okay. So
part.
the parts. Let's do that. Let's just throw all caution and sanity out the window, and find.
Can I still complicate it with my solution?
It's
Find.
actually,
I was thinking of something else. That is, first go for the zeros. Find
they first came for the zeros.
first.
Sorry.
And when they came for the 9s, there was no one left.
For the zeros. Now first go for the zeros and find this pattern.
Yeah.
And the moment you find a number, just add 11 to it and another time and another time and another time and count how big the family is, and stop of course the moment that you have 3 misses. But it is at 11 because you have the pattern of 11.
No, not 11. Either 11 or 110 or 1.
Yeah, that is the other pattern. That is the pattern of 101. You find the numbers with 0, and of course you don't find a prime with 0 at the end. But the moment you get to this one, the 110, you find the one with 2 zeros before the last digit. And then you add 110 and check it, and another just add 110, 227.
No, that's I mean, that is
6,
we are considering so many cases. That's what he's trying to solve with regex.
Yeah, but it doesn't apply because you can only have a 0, and then you do, and the ones that did not have the 0. The zeros you can, but you need to try the 1s and the 2s and the 3s. And if you have 2 misses, you get to 8 hits. Yeah. The moment that you get 3 misses, you have to step out. Then you go for the 1s again. And for the 1s, you can only have 2 misses if you go up.
Yeah.
I guess I should have done split. Because now I realize I also have to do /d append depending on the number of occurrences. Num pluses. So parts. I guess the backslash and the backslash is gone because I guess I don't know. There's something wrong with this.
You have Japanese.
Yeah.
His girlfriend that is Japanese.
I don't know.
Sometimes borrows his laptop.
Nobody is borrowing my laptop. Okay, so this is kind of, times replaces.
Yeah.
Okay, so this is partially, I guess we have to figure out what the parameters are for this.
Yeah.
So what is, do you know by hand? Probably not. Open. So we have isn't it permutations?
No, combinations enough, right?
Combinations is other.
Okay.
You have the combinations range 4, 3. There it is.
Yeah. Okay, fair enough. But it always has to have a /d in it, right?
Yeah.
Otherwise, it doesn't make much sense. Okay, so we're looking for number places.
Yeah.
And I guess, oh god, this is so wasteful, but I guess.
I think we give this up.
Yeah.
As I said earlier, we should time box it.
Yeah, okay.
Because it is just a tedious hour of typing the everything we thought of into a program.
There's nothing interesting about this? Okay.
No,
This is very interesting. I find this actually very interesting.
I came for the number theory things, like that someone of you just tells us, yeah, but all primes that have that all primes have differences with other primes that are modulo another prime or something.
This is what you're here for.
Yeah, that is what I expected. That someone comes up.
I knew that I wouldn't be sitting here. If I could find patterns in primes like that, I wouldn't be sitting with you guys.
No, but
with the fields middle
no,
of
Euler
mathematics,
that's
€1
defined
million
of the PSA stuff that you do primes. If you have primes and you multiply then and then you can shift along and you still got a modulo of that product is always the same. That such things, but I don't know if there's something applicable here. But of course there are things in primes. Otherwise you would not have to.
No, I mean,
otherwise you could just do the same thing with Fibonacci's. Yeah. I mean, what is the difference? Why prime? If it would be Fibonacci, why?
Probably would not make a difference, I don't
Yeah.
think.
For us, it would make
Or just take all number plates of Germany or whatever.
Yeah.
So there is no.
There's no meaning behind the primes,
No.
for this problem.
I would expect if you do the thing with primes that you need to use some special aspect of primes.
Maybe they were just lazy when they were formulating this problem.
They just needed a collection of numbers, probably.
Or maybe not, I don't know.
No,
Maybe.
because you need the primes to achieve this. Because you want to find the first number of 8 prime value family. So it wouldn't be any.
No, as he said, that could be number plates of Germany. Number plates of Germany, in a way, when you replace this, there are eight numbers which come from Hesse, for example.
Yeah.
What?
Number plates.
Yeah.
Car number plates.
Or only the letters in the number plates.
Yeah.
Find the family that have MK. in
But
it.
here you don't know the number of numbers that you're gonna change and the number of the total length.
Yeah, but there is also no relevance in the fact that it is the primes. If it would be the Fibonacci's and there is some website with all different numbers that you could.
Yeah, instead of primes, they could have given just a list of numbers
Take
with no connection.
the digits of pi.
Yeah.
Take the digits of pi and find where a double digit is repeating itself every 10.
You know,
digits.
I'm pretty sure I have this one solved. I think I have all. Maybe this is one of the ones I don't have solved, but I have most of the ones below 100 solved. I wonder if I can. Yeah, okay. Should we cheat? Is this maybe?
We don't cheat. We will see the number and we will read through the comments, but we will not complete it then.
Yeah.
The moment we do that, we will kind
cannot
of
count on ourselves.
fail.
Yeah.
Okay. No. So this is where
Weird stuff.
this is where the issue is.
You know what?
Try 8
His
2 3
password
8 5.
is
Yeah,
that
the
first
length of
number.
password. Huh?
The first number which we have to find is his password.
Yeah. That's the first challenge.
Forget it. No, we're not going to do this.
Why?
Because I will have to go through the login process, and that's too
Tedious.
it's too security issue for me.
You can
There's
like
something for
unplug.
YouTube.
You can unplug the and pass the.
Well, but the stream is also
You
running.
can pause.
It's being on the internet.
You can pause it then resume after entering.
Yeah, we can
Forget
cut
it.
this too
Yeah,
now.
it's fine. We
how
can
to
still
stream.
go through the forum, right?
No,
No,
only
the
if
forum
we
is hidden behind. You have to get the solution first.
I see.
Otherwise, you can solve the Euler.
I guess we can just look for.
Ah,
But that's not. No, I don't want to do that. Okay, well.
Area 51 solution.
I think if we want to do another one, I will have to log in anyway, so probably. But maybe we don't want to do another one. I don't know. How are you feeling?
We will do another one. We should finish one more. It's 9:48.
Yeah.
yeah.
We should at least finish one.
We finished one.
We finished one.
Yeah, that was the
Popel. Yeah. Okay. Then I guess we declare. What do we declare? Die Kisten, die weiße Fahne. Or do you want to keep that? I guess. Give me one of them that is not.
I never want to see this.
Oh, everything is.
I never want to see this paper.
Yeah. Okay. Okay. Nummer 20. Warte.
Problem 87.
We solved this, didn't we?
No.
Okay, we haven't.
It's again a programming issue.
Okay.
And then
You feel cheated.
Isn't it like while while less than 50 million check for primes?
The smallest number of expressible is the sum of prime square prime cube prime fourth is 28. Well, 50 million.
It's just
We'll have to go.
50 million complexity. That's it.
Well, but there has to be. This does sound a bit more number theoretical. Like you could see a pattern. Wait, did I think I copied this wrong. No, I didn't. Is this a typo? No, it's not. The sum of a prime square. Ah, yeah, okay.
Yeah, seems like combinations.
Yeah.
Yeah, just start documenting by the next prime.
Next prime, yeah.
Yeah.
Uh-huh.
And do combination. Like get the list of primes
yeah, and try them all.
and
Yeah.
while less than 50 million.
2 to 2,
just
2 to 3, 2 to 3, 2. Like that.
why it's harder than the other one.
It's 3 dimensions. You
But
have
it's
the
not that
dimension of
meant.
the
But
two,
it's
the square, the dimension of the
Cube.
the third part, the cube, and the fourth.
Why dimension not 3 dimension?
No, what he's saying is, we take the primes and go in the direction of squares. One is in the direction of cubes, one is in the direction of to the power of 4.
3 dimensions.
Yeah, then
And-
we
and-
slowly like grow.
And how many numbers?
everything below
How
50
many
million.
numbers? You just how big is 50 million? Take the fourth root of that. 50 million.
5 to the power 10 to the power 6, so square root is 10 to the power 3.
Yeah,
Yeah,
1,000.
so
Yeah,
2,500.
less.
And square root.
No,
square root,
less. 50 million.
Is this?
Yeah,
What is the fourth root of?
Is this? What is it? 1 to 5?
That
Yes.
could be.
This is 8.
45.
Well, but pardon. Wait.
Fourth root. It is a quarter. So
1.25.
the 0.25.
No, but that's cube, isn't it? I mean,
50
0.5
million.
is squared.
No, 50
Square.
million.
This
Uh,
is this
square
is
root.
root.
This is square root.
Yeah.
And now
25.
25 is fourth.
Yeah, but
And
There's
50
third.
million. No, this is a fourth of 1. The 0.25 is 1 over 4.
Yeah.
45. 84.
But I don't. This doesn't.
84. So this.
Are you sure?
This
What
one
is the
can
cube
go,
root?
Can go up to 84. That means, and you
Cube
can,
root is to the power of 1 by 3.
Let me just see.
and you cannot. So you need you can fill in all primes until 84, and then you start with the 3 powers, and with each of these, you can fill them up with all primes until, and that is all primes until to the third.
No, that's what he said. We'll do all
That's
the combinations.
over 120 or so. And then that's all primes until there. And then these combinations all primes.
Well, we
No.
can. We
That
can.
is
We can
until,
take, as I said,
until
we can take all the primes up to 84 and make all the combinations of 3 sizes. Do this math, and if they are a number,
no, it's more.
We
it's
need more than 84
in
primes.
the second power.
Yeah.
You need to go up to, of course, 7,000 or so.
Yeah.
So a bit further.
not 7,000, 2,000.
No,
Yeah,
because
8,000.
we-
Yeah, okay, yeah. Roughly
Yeah.
7,000, yeah.
What? 7,000.
7,000.
Yeah.
So you need the primes until 7,000, but the fourth power can only go until 84. And then you have them all, and you need to list them all in
And what is the
an array.
cube?
and
0.33?
then-
0.33, yeah.
Okay.
Yeah, but that is not like that. You need to yeah, that will be okay. Now it will be
Maybe you can do 1/3, 1/3.
Yeah, 1/3.
I think
Is it the same
slash
number now?
binds faster. Yeah. Binds more strongly.
What is-
Okay, it's good enough.
What is strong? Strong.
Here, what is operator precedence here?
Yeah, power is of
I
course
think it's
strong.
from the left to the right.
No, power is strong.
Well, and this is why I put the parentheses, because I don't want to care.
Give it a try. I want to see it. If Python really what this is, yeah, like that, of course.
There's 2 stars, you mean?
Power,
Power.
raised to the power. So 2 to 4, 16, or something like that.
And is there no solution in logarithms again? No. And then you have all combinations, and then you need to check the doubles. Again.
Why check the doubles?
Because you say you find 50, but it's 53 till the fourth, and you have 29 to the third, and actually, there could be no doubles.
There could be doubles because of the primes.
Yeah.
What do you
If we have 4 to the power 2 and 2 to the power 4, yes, but 4 isn't there.
There could be doubles.
doubles of what? You
Could there be?
mean from 2 and
Because it's just simply plus, so 5 to 2. Of course there is a double. Oh no.
I think just we do
No,
is,
because you only have primes.
Yeah, that's
You don't use 4, so you cannot have this one exactly matching the same another number at
power 4, yeah.
power 4.
I guess I need to do +1.
They forgot.
You already took the seat, right?
They forgot.
Then you
They forgot the series 1 to the 4th.
Yeah, you're right.
they said primes.
They forgot. Yeah, prime.
1 is not a prime.
1 prime.
1 is not a prime.
Okay. I'm too old-fashioned.
Is this a? Oh, I don't. Okay, forget. Sorry. I didn't ask anything.
So at least I've learned something new.
Okay. What did you call this? They call this the.
Oh, you already have it. Yeah, that's all.
What do they call this? Doesn't this have a name?
The
Sum of prime. Okay.
this,
sum.
Power, prime power triple.
the number. The number.
Let's call it X.
The candidate number.
no.
Okay, well, but I need to do, I guess, time. I guess we.
No, it's the other way around. You need to, for each power 3, you need to determine a new maximum. Or just find out if it is less than 50 million. Yeah, of course. Same. But now you're counting lots of.
Yeah.
You're going to 7,000.
I guess let's do. Let's call this num4, and the power4 is the num4 to the power of 4.
You know, this is better. And also num3.
I'm not that fast.
Fast enough.
Super.
I think.
Now you can remove those powers.
Yeah.
And add that to an array.
Probably better to a set.
Well,
So if there is any clash.
why do I need to keep these? Do I need to keep these?
No, you can check whether it's less than 50 million, then we have a count.
And I would see that if there is a clash or not. I still doubt
I
that.
think we do.
Maybe there is something with. No, there could not be anything.
How or they do want the number of things?
Yeah, how many numbers below 50 million?
So no option that 17 square
Oh yeah, that's a good
plus
point.
plus 53 to the third is the same as say 47 to the third and 23 square. Is there really no possibility that something like that can happen?
I guess if we
Why x is less than 50 million, we do this.
because
Just add it to a set and
could it be that it's larger? I'm not sure if it can be larger.
find it in the set. Find it in the set also.
Why?
It could be larger, can't it?
Yeah, of course it can be large.
Yeah.
Because you do them all to the max.
Yeah. It can be larger. I can pick if I pick the max
Of all three,
Yeah, for all three, then
close to
it's-
150 million.
Yeah.
Also, if it's larger, I could probably exit early.
Yeah, for the twos.
For the twos only.
Yeah, do for num2 in range, and then you do count to 4 and the 3 already together, because
So
that's
here
not,
I know
not so many.
here I know it works, right? But why? What can I do it here?
You count the 3 and the 4, and if they are already over
Yeah.
50 million.
I guess this won't be nearly as common.
Yeah, that will be a lot,
Yeah.
because for the second half of the 3s and the second half of the 4s it is already going over.
Maybe we do continue, otherwise we add it to the set. Because the question is to how many numbers we verify this.
Yeah, but you want to do continuous somewhere. Where?
There.
Oh, not break.
Otherwise we
Not break.
add it to a set.
Not break. You need to add it to a set. So you only do, if power 4 and power 3 is less than 50,000, you do this section for number 2.
Yeah, that's what he's doing with break.
Yeah.
Yeah, it stops here.
Yeah.
If it's greater, we stop.
Oh yeah, of course, yeah. Yeah, of course.
Atev, okay.
Yes.
That's fine, yeah.
Where we add
And now break, and now what happens if you find one?
Yes. So that's the question. I guess we want to count something, so it's plus equals, I guess.
Yeah.
But we need to think about the duplicates.
Yeah, just
Duplicates are very, very
Maybe
unlikely, but
we
I
do a
want
set.
guarantee.
just do what
Okay,
is-
we do a set. Let's just not.
But we are talking a set of the size of millions.
No. 50 million, and I guess there's only 4.
Well, combinations. We're talking at most. What is it? 8,000 times 300 times 80, or 7,000 times. You know?
Yeah.
Yeah.
Could be log 50 million.
Okay.
No, because half of the 2s is falling out.
Huh?
There's a lot of numbers for it.
Okay, well, besides this, we
More of,
actually need to
let's-
check if x is actually a prime.
There is
If
a lot for
x
that. I guess it's only.
prime
For 50,
set.
it's only 4.
We
I guess
we don't need
average.
that.
You need to do
We don't need
average.
that whether it's in prime.
Average 3,500.
Any number.
Average. What was for the 3? It was the third.
For 50, it
The,
was
the,
for
the
num-
list has to be prime. The num4 in range, not 1 to max power, range of prime number. That should be the prime numbers. It's not the whole range. That's where the
These
prime-
nums have to be prime.
Yeah, exactly. Not the last.
Okay, fair enough.
That makes the numbers much less.
Yes, it does. Okay, fair. Okay, so I guess we have to do then if num4 not in prime.
No, we do it the other way around. In the range of the prime numbers, you find that max power 4.
Is it the power? It's not the power, it's the num. That has to be prime.
Yeah, it's a number, not the power.
Num
The
4,
power is never
num
prime.
4 in the range. But that's not the range that you need the prime range until.
Yeah, let's do, we just go, we do, let's just pull this up here and do power 4.
Or maybe we do prime and we slice it to that max power 4.
Oh, this is the best, and you don't need to do max, just prime range.
Yeah, prime, save, prime list, and we slice it to the max power 4.
I don't feel like
And you
slicing.
have you have the, once it goes over 50,000, it's.
I think if I want to slice, I need to know its index, right? And I don't care a lot. I would just as well break.
Okay.
Yeah.
I would just as well break.
Yeah.
Okay, so then the prime list. How many do we need?
7,000, 70, 100, 8,000.
Let's do 8,000.
No, not 8,000 primes.
Well, up to 8,000, which I don't know.
Oh yeah, of
I
course,
guess
that is
4,000 or something.
sufficient.
Up to 10,000, we have only 1,200 primes.
Wait a minute. Yes.
Yeah, but it doesn't matter. It stops when so it does not use more.
Okay, so and then we want to. How many numbers below 50 million can be expressed as the sum of?
I guess it will be over a million. But,
No, it can. What? Yeah, maybe. Okay, fine.
is there a way to check doubles?
Well, this is a set.
Yeah, but no, you don't see it if there is a double. No. Is there a way to check? Whether
You are
it's already
correct.
in?
You are completely correct. Then I guess we do num4, num3, or num.
Whoa.
No, we add the sum of them, the power.
Well,
No, he's
X,
adding
we add
the
x.
he's adding the numbers which created them.
yeah.
Yeah, and
Well,
the end and the total, of course, the x too.
Why?
Because
I mean,
you
that
also-
doesn't.
Because
I
you
mean,
want to
this.
see
These
whether
are
there is a double.
these are equivalent. I mean, this produces the x. So
No.
This
Yeah.
produces the
But now
including
you
the
have,
duplicates.
now you have including the duplicates, but I want to see if there is a difference between the including duplicates or the not including.
We cannot see that because that will be a huge list.
Yeah,
We'll have
make
to
them,
print when there is a map.
take them two, take them both, and then just count the numbers in the set.
Maybe
I
we
just want to
create
see-
a list,
see
then
if
we
this
convert
set-
it to set
No,
to view the
You do the nums add for num,
a moment to think.
the nums add as individuals. That is the total, including doubles, and you do another set with only the x's. That's
Do you want to type?
nums the nums without and with duplicates.
Okay. Let me think.
See if it works. 5. And now we don't need x. Yeah, and
no dupes.
now with the x. Now with the x only.
Well, let's see. Oh yeah, list. Let's just do list. Yeah. No loops.
Yeah, but now you
No.
you have not allowed the duplicates. Now you do the nums with only the x as result. Adding
This is
it.
how
No,
many?
only the x. That allows for the duplicate. Now you're still not allowing the duplicates.
You are okay.
Yeah,
Yeah.
now you're removing the
Yeah.
duplicates.
Okay, fair enough. Fair enough.
Now we have to make it set. Now we have to make it a set.
Well,
set.
it doesn't matter if it's
Yeah, set.
it's any way which way we do it. I'm sure this is because of the prime
Yeah,
things.
there are
that-
no duplicates basically.
5, 4.
The prime. There's always a unique prime factorization.
But this is
Oh, but
addition.
this is
No.
addition.
But this is But this is you can read this as 2 times 2. No, but this is no. This is addition.
addition,
It's
yeah.
addition. It's addition.
Yeah.
Okay. Okay. Well, now I do actually need, I guess, to
Login.
log in, and I guess. Okay.
No, only I can see.
Oh, that.
If you want to type in the password.
Is it indicated as dots or not?
No. He probably has to read it from. I don't know.
From the file.
No, that's not it.
Can you type it right? Or does it show for a second?
I'm not sure.
Yeah, it showed it. You see, but it's too late.
No, but his fears are really warranted. It's genuine. I wouldn't do it either.
Okay, what are we on?
548.
Let's see if the stream.
And what was recording the stream? What was with which devices?
Well, I'm hoping that. Oh, this is just screen recording.
yeah,
So here.
yeah, but you have typed it in that screen recording. So, oh no.
No, this is what I clicked here. Display capture. So I can display capture. Just off. On.
Oh no. Okay.
Okay, we were on problem numero
87.
87. So we are we said 587. 548. Who would have expected? Is incorrect. So how many?
Well, can you show the prime list?
Sure. This is
We
not
don't have 28.
well.
This is the outcome.
Yeah.
Is it below or equal?
Yeah, but I guess that 50 million itself is not. You check
Why
the
not?
bottom of the last. You check the last one and see if this.
Oh, the last one you want to see. Okay, wait a minute.
Well, even the first one is wrong.
Well, why is it wrong?
We don't
Oh,
have
yeah.
28.
No, we do not have 28 and 33.
Right.
Where did we start? Prime list.
Good. Oh.
Consumed.
Oh. Yes. Correct. Yes.
Almost a million. That was.
Now we have to do this whole experimentation again. Yes. Okay. So there are
Lots of
duplicates.
doubles.
There are duplicates. Yes. Okay. Okay. Let's try this. I think this may be too soon. Nope.
Huh?
Let's see. Nums is a set.
Show the first 1,000 if that is possible, or the first 10. See if that 28 and so are in. Yeah, that's 49, 47, and there is no double. No, of course you have
98. Yes.
Yeah, that's not a prime.
What 98?
What about it?
You wanted to say that. The 49.
And then look to the 28.
49 is also not a prime and 33. This is a whole totally wrong problem. This problem does not. Only 47 is a prime.
Probably wrong. 73 is a prime.
Okay, okay. Can we solve this? Do we get this correct solution for this? Let's see. In fact, there are exactly 4 numbers below 50. So
One. MK primes, does it create 4,000 primes or the primes up to 4,000?
4,000.
Okay, just want to know.
Yeah.
Just fill in 8,000. To be sure.
Fine.
Okay, there's a difference. So not up to 4,000.
Limit.
Oh, yes. No.
But it's not looking at the limit.
Yeah, it's creating up to 8,000 limit. Then it's doing the save. So it's up to that.
You are correct. I always write this function so that it does a number of primes, but this one apparently doesn't.
What?
This is the max prime.
Yeah.
Okay. Let's see. I always write this function differently. I assumed incorrectly. Okay, fair enough. Then this is then the solution, I guess.
Third one is the charm. Yes.
Yay! Woo!
Okay,
And 98 is included.
Analysis prime factor.
Okay.
What was it? The difficult.
Can we look to the 51 solution?
Well, this is the Euler FFF.
I found the solution for 51 is on the internet. It's on blog.
What's this?
It's not.
This is the solution for the 87. Or the solution.
No, the first comment. What is code? What was that?
Whoa!
J?
Is that really giving the solution?
Up here.
Oh,
Up here.
that is nice. Is that really? It looks worse than.
I think it's up here or.
APL. Oh, Jesus.
Yeah.
Not APL.
Influenced by Euler.
Yeah.
Okay, no.
But
But.
yeah, it's 19th.
Is there a. I wonder if there's an.
Yeah, but can you still show it? What was it doing? Because it looks like he was not doing a loop, or he is doing.
He's doing a loop.
Is that the?
Okay, here, this I believe is the 50 million. That,
Yeah.
that I can read.
Yeah.
You can hear it's the power.
And that would be,
Two,
and that
three,
would be,
and four.
and that would be even
Yes.
one character shorter if he used 5E7.
Yeah.
Correct. He's being wasteful.
Yeah, he has wasted a lot of
Here, this is a smiley.
whole 8%. There is nothing, and there is angry.
No one with brain fact language.
What
Probably.
is that one with? Whoa, this.
TCL?
Yeah, and tickle is.
What? You can write boxes in TCL?
It is
Turing? What?
Okay. What has more thumbs up?
Oh, another one
Another
with
J.
G.
Oh, jeez. Why are you so obsessed? Who
No,
cares?
This is more
Readable, yes, it's
It's
very
more readable.
This is structured programming.
yeah.
What is there no one who solves this?
Yeah, I want to look at the thumbs up because usually that is some marginal indication of readability.
No, that looks worse than bad.
Come on, there has to be some. Okay, here.
Start.
Fine. Yeah, this is like, get me out of here.
Exit.
Rotations.
Oh, he's doing all combinations. Stupid.
Really?
Stupid. It's not even necessary.
I don't know. Yeah. Okay. Is this all part of the same solution or are these individual? No, this is part of the same solution.
Well,
Yeah, this is like too much.
Yeah.
What the? He's producing code. An eval. Jesus Christ.
Also nice.
from
Generalized solution by Lausman.
Oh. Arbitrary primes.
Oh God, jeez. He's just bored.
Yeah.
This is what we're looking for. Not what,
Not even that.
isn't it?
Less than 5 times.
He do it
Oh, yeah,
then
okay,
for
yeah.
3, 4, 5, the power of 3,
No,
4,
no, no.
5.
Well, he's doing more powers.
Yeah, yeah.
Right.
Yeah.
There's 3, 4, 5, 3, 4, 5, 6, and so forth.
Yeah, from the sys exit you can understand.
Yeah, but from the sys exit.
Yeah.
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 The brackets you can understand. No,
Why does this have so
and why
many
did he
upvotes?
not find an overlap between these?
No overlap? What are we looking for?
I mean, does anyone else mention? Was there now a difference between the 1097343 and if you count them all separately?
Yes. I think
At
so.
the end,
I think
at
so.
our total end solution.
Yeah, I think so. I'm pretty sure. Yeah.
Yeah. There are a few.
And I would like to see which those are.
Okay. I guess we do.
There are roughly 100,000 of them.
Do is it's over 100,000.
I guess we do.
Just find the first one and then stop.
Okay.
So nums is then the set and just find if it is already in the set. Print and break.
Well, I have to break.
Print what?
I have to return because break only goes one level.
Yeah. Or you can import sys.exit.
Well, I don't want to kill the kernel. There's a.
Yeah, but break is also sufficient because then you also reduce. Then you only skip for the number twos. That is also that reduces also a lot. No, that doesn't make it less.
Import shutdown button.
Okay, we wanted.
The powers.
Power off.
No, also the num2, the num3, and the num4, and the power4, and
Not the number.
the powers 2. Oh.
Yeah,
Two
but we don't know
five,
what else made that. We know this is the first conflict.
Yeah.
Yeah, no, this is the first one that had a double. You need
Yeah.
So there's some
to-
other way to reduce 1, 4, 5.
Yeah.
Yeah, just do it the other way around. If x is 145,
Wait, no.
just do if
three,
x is
four,
145, then
five.
print it and not return.
Okay. Sure.
And 2 to the power of 3.
5 to the power 3 plus 2 to the power 4 plus 4 to the power 1.
11.
Wrong.
So 2.
2 1.
2 to the 4.
11 to the power of 2,
16,
2 to the power of 3, and 2 to the power of
8,
4. Yes?
And
Yes. Already see it.
121. Yes. 145. Yeah, true. Yeah, the computer is correct.
Wow.
Okay.
But it was even less. They both had a 2 at the 4th power. So it is 11 square and 2 to the 3rd is the same as 2 square plus 5 to the 3rd. Yeah, 130 and 129.
1.
Oh, there's also 100. Yeah, both 100.
Okay,
Both 100.
I am declaring victory.
3 problems.
I thank you all for coming and for participating, and I hope to see you again.
Thank you for organizing the event. This is the next step.